All right, I hope you had a good Labor Day. We're back. You just submitted homework number 2, right? Okay, so homework number 3 will be posted on Blackboard immediately after class. You've got a week to solve that one. So it's due on September 11th by noon. Today we're going to be moving on from Chapter 1 in the textbook to Chapter 4. And we're going to start dealing with some more complicated problem solving where we'll have to use Microsoft Excel for some of the problems. And so just as an announcement here, please bring a laptop computer to class for the rest of the semester. Something, or an iPad if you're able to run a spreadsheet on your iPad. You're going to need access to a spreadsheet for many of the class meetings for the rest of the semester. And so if you don't have a laptop, you can borrow one from a friend or check one out from the library. But you'll just be staring at the wall doing nothing if you don't have a spreadsheet available for a lot of our class meetings. And so it's really important that you bring a computer to class. Any questions about that? All right. Let's just review, since it was a long weekend, what we saw with gradients on Friday last week. Remember, a gradient is something where the amount is increasing or decreasing by a constant value each year. So here's a gradient where we thought in terms of a strategy because this cash flow diagram had both an annual series and a gradient in the same cash flow diagram. So what we did was we found the present value of the annual series component, and then we found the present value of the gradient and combined them together. And I'll just remind you of the fact that with the annual series, there's nothing in year 0, and then you see the first annual series amount in year 1. Whereas for a gradient, there is nothing in year 1. So it's 0G, 1G, 2G, 3G, and so on. All right. So strategy. You just have to see a complicated cash flow diagram and think about what are the steps that you're going to take. And we also talked about what you do when the gradient doesn't begin at time 0, like where you've got many years in the future, the annual series and the gradient. So over on the other whiteboard, I kind of wrote out maybe like a pseudocode or a summary of the steps that we'd take in order to find the present value of these amounts. And so just to refresh your memory on what that process may look like, for example, if we have a gradient here, you can see that we would first find the value of that amount as a single lump sum in year 3. So year 3 is what we would treat as a quasi-present temporarily to consolidate the gradient into a single lump sum. So you'd find the value in year 3 using the find P given G, either equation or factor table for whatever the interest rate is. And then as the second step, you would then take this lump sum in year 3, which actually is a future value. See how I have P in quotes there? That's just to indicate that we're treating it like a present value, but what we really know is our present is here at year 0. So this single lump sum at year 3, then we would use find P given F to discount that further to year 0. So anybody have questions about what I mean when I say strategy or putting together just a summary of what your steps are? I think it's a good idea for a complicated cash flow diagram to write that out before you start your calculations. If you just jump straight into the calculations without having a written summary of the steps, it's a lot easier to make mistakes. So I suggest that you take the time to kind of summarize the strategy for yourself. And also it helps the grader to understand what your process was, so you can get more partial credit if you happen to make a mistake in the calculations, if at least you had the main idea correct. And it's the strategy part that's maybe worth more points than plugging the numbers into the equations and operating a calculator. All right. So Keep in mind that the interest factors, you can always use those regardless of whether you have a nice round interest rate. You know, sometimes the interest rates you'll be given would be 5.25%, and you're not likely to find a factor table for those, and so the interest factors will always apply in situations like that. Okay, well, here's a picture of some nice balanced rocks, just to set in your mind the idea of equilibrium or balance. So here's an elephant that's balancing, and in engineering economics, sometimes we are interested in setting the present value of the inflows equal to the present value of the outflows. And the reason why we care about that is that's how you find the rate of return for a project that you're investing in. So if you know, for example, that it would cost you a certain amount of money to buy some equipment today. Let's say that you have to pay $23,000 to buy some piece of equipment. And you know that if you do that, you're going to have 6 annual revenues of $5,000 each. So you'd want to know what's the rate of return on an investment like that, because you could take the $23,000 and just put it in the bank. You know, if the bank account that you have access to is paying 4% on deposits, is this better? How do you find the rate of return when you know what the inflows are going to be over time? So the way that you find the rate of return is you discount these inflows to the present, and you have to find out what interest rate would make it equal to 23,000. So what I'm saying is we can, in our note, our kind of shorthand for summarizing problems, remember when we put things in parentheses, statements in parentheses, 23,000 is equal to 5,000 when you find P given A at some unknown interest rate and for n equals 6. So we can see, we can count them up. 1, 2, 3, 4, 5, 6. So you're going to get $30,000 over time. So I'm not saying that 23,000 is equal to 30,000. What I'm saying is that there is some interest rate where if you discount the future revenues at that interest rate, it's economically equivalent to 23,000. So what is the interest rate that would bring balance between the inflows and the outflows? Anybody know what the interest rate would be? I'll show you how to solve it. There's 2 ways I'm going to show you how to solve it. One is with a website called Wolfram Alpha, and another would be using Microsoft Excel. And I'm not a power user of Wolfram Alpha. I usually put things like this just into my calculator, but I can't project my calculator onto the screen, so it doesn't work well for demonstration purposes. But if you want to follow along, you can go to Wolfram Alpha as well. What we're going to put into Wolfram Alpha is the P divided by A formula. So from the equations here, what is the formula for P divided by A? It is P divided by A is 1 plus I to the n power minus 1 divided by I 1 plus I to the n. Okay, so we know that P is 23,000. A is 5,000. 1 plus I to the power of 6 minus 1 divided by I 1 plus I to the power of 6. So we've got only one unknown in this equation. What is the interest rate that makes 23,000 divided by 5,000 on the left-hand side equal to that ratio on the right-hand side? Okay, so Wolfram Alpha, we can just try and type in that equation. So 23,000 divided by 5,000. I'm going to use the arrow key sideways is equal to parentheses 1 plus, oop, didn't get the parentheses, 1 plus I to the power, I'm using the shift 6 to do power of 6, and then the right arrow key to get out of the exponent, minus 1. And then I'm going to use shift and the left arrow key, I hope, so that I can tell it that I want all of that to be, oh, I screwed it up. I'll do the divide this way. No. Let me copy this so that I can paste it into the divide. I thought earlier when I was setting this up, the divide worked for me, but apparently not. Okay, so I just pasted that into the numerator of that equation. Okay, now in the denominator, it is I times 1 plus I and to the power of 6. Okay, so I think I've written that into Wolfram alpha correctly, and when I click on this, it's going to solve for I. Now, it gets a little bit confused with the variable I. In a moment, we're going to tell it we do not mean the imaginary unit. We mean some variable called I, because down here it's saying the result is false. So no, it's misunderstood briefly. So I'll say it's a variable, it's calculating, gives us a graph, blah, blah, blah. The answer is 0.0816. So the interest rate is 8.16%. 8.16%. So that means you're earning a rate of return of 8.16 if you make a deposit of $23,000 and then you get 5 payments of $5,000. Then you have balance between the inflow and the outflow. That's called the internal rate of return. We'll get into the specifics later, but that's how you solve for I using Wolfram alpha. The other way to do it, with Excel, we can say we're going to have some guess of what the interest rate is. So I don't know as I start, so maybe it's 1%. I'll just put in some guess value for I. All right? And then here I know that the calculated P divided by A is equals 23,000 divided by 5,000. So I'm looking for a ratio of 4.6. So 4.6 is what you get when you have 23,000 divided by 5,000. So that's my calculated P to A ratio. And the goal-seek P to A ratio, I'm going to type in the formula now. So you type a formula in Excel by doing equals. So equals, and the same thing I typed into Wolfram alpha. 1 plus, and now instead of writing the letter I, I'm just going to click in the cell location that has this value for I. 1 plus I to the power of 6, and then minus 1, and then I'm going to put parentheses around all of that, and divide by parentheses I times 1 plus I to the power of 6. That's a little hard because it's not building it visually in the same way that we write it. So you have to get accustomed to the where the parentheses should go. And I make mistakes on that from time to time. You just have to do your best and make corrections when necessary. But what this is going to do is it's going to tell me the ratio for this guess value of 1%. So let's see if it calculates or if it gives me an error. All right, so it's saying if you substitute in 0.01, okay, so I and then P to A. 0.01, it's telling me the P to A is 5.79. Okay, well, what if I change this to 0.02? 0.02, it's telling me 5.60. Is that closer to the goal of 4.6? Yeah, we're headed in the right direction. So let me try 0.03. So for 0.03, it's giving me a ratio of 5.42. All right, 0.04, getting closer, 5.24. So if you're a power user of Excel and it's driving you crazy that I'm just typing these values in one by one, what's the efficient way to finish this up? Matthew? Goal seek. Right. Oh, it's here even. Goal seek. Yeah, so there's this tool in Excel where you can say, instead of me manually putting in the I value over and over again, just tell Excel, hey, keep changing I until this is equal to my target of 4.6. So here under the Data tab, Data, What If Analysis, Goal Seek, I'm going to say, set this equal to 4.6 by changing I. So I'm giving it permission to put any value in cell B1 that's necessary to get the target cell of C5 equal to 4.6. And so I'll click OK, and as soon as I click OK, the numbers are going to change really quickly, and in less than a second, it's going to tell me the interest rate that we already knew, 8.16. So that's what we had calculated with Wolfram Alpha. Excel tells us the same thing. It's just another way of solving an equation for the unknown I value. Does anybody have any questions? All right. So a little bit of numerical solving methods here. Balance. We're going to want to find what interest rate gives you the present value of the inflows equal to the present value of the outflows. And so this cash flow diagram, if you discount the revenue to the present, it's like a single big arrow up at time 0. So what interest rate would make it so that the economic equivalence of 5,000 as an inflow discounted to the present is equal to 23,000 as an outflow, which is already at the present. Okay. So finding the unknown interest rate. All of the values that are in the future, you'll discount them to the present and combine them with the amount that's already at the present and keep changing the interest rate until the present value of the inflows equals the present value of the outflows. So that's what we did with Excel. Let me show you another way. Year, amount, PV of amount. Okay, so, and then I'm going to have here a guess value of the interest rate, starting with 1%. So year 0, 1, 2, 3, 4, 5, 6. Our cash flow diagram had negative 23,000 at time 0, and then 5,000 each year after that. So I'm just making a cash flow table, 5,000, and I don't have to type that in over and over. If you just have a value here, you can drag it down like that. Okay, the PV of the amount equals PV of, I'll use this interest rate. I'm pressing F4 to anchor the reference, as it's called. With these dollar signs, it'll know to always look in cell B7. Even if I drag the formula down, it's always going to look in cell B7. Okay, number of periods, that's just n, which year you're in. So I'm in year 0 for this row, the next row I'll be in year 1, and so on. Okay, comma to skip over the payment field, and then for the future value I'm going to put the negative of the amount. And I'll tell you why I put that negative sign in a minute. But like 23,000 is already at the present. So it's already at the present, so the amount is not going to change at all. But if I drag this formula down, what it's doing is it's telling me what is the present value for each of these amounts. And then if I find the total by adding everything up, what I want to do is find what interest rate makes the inflows and the outflows equal when they're all discounted to the present. So what interest rate would do that? Is it 2%? No. Is it 3%? No. Is it 8.16%? Pretty close. We want that to be 0. And so I could do goal seek again. Data, what if analysis, goal seek. My goal is for this cell to be 0 by changing the interest rate. 8.16. It's just done it to more digits here. That's a preview. We're going to come back to this method that I just did. I'm going to go through it more slowly in the future. So don't worry if you don't have your computer here today or if you didn't follow every single step there. But what I'm doing is I'm just emphasizing this idea of balance. What I mean by balance is the inflows and the outflows are equal when everything is discounted to the present. Any questions so far? Keep changing the interest rate until the present value of the inflows is equal to the present value of the outflows, meaning add it all together and the sum is 0. So back to Microsoft Excel. You know that minus sign that I put into the formula? It's because Microsoft Excel automatically assumes when it's doing financial calculations, it thinks that if you're using those built-in functions, it assumes that the kind of problem you're asking it to solve is if you have some future amount, how much do you have to deposit today to have that future amount available? So it always returns the opposite of the input value, the opposite sign. So if you give it an inflow, it will tell you an outflow. So the built-in function automatically changes the sign when it's doing the discounting. Or if it's doing the compounding, it also changes the sign because there's a PV function, there's an FV function. And anytime it's doing financial calculations, if you actually want to know what is the discounted amount but not the opposite sign, then you have to put the negative sign into the formula. Because by default, it's going to change the sign. It's going to change the sign because it thinks you need to make a deposit today to be able to do a withdrawal in the future. So it's no big deal. It's just something we have to keep in mind, is that it's automatically going to change the sign anytime we do those calculations. So we just have to account for that. All right, let me give you today's in-class exercise. Okay, so on the paper I'm giving you, A, B, and C you can do on paper, using the factor table that I've provided. D and E, I'm going to demonstrate in a few minutes, but if you have your spreadsheet today and you want to try it out, go for it. I've kind of already hinted at the method that we're going to do for part D. So if you want to give that a try, I'd be pleased to have you, implement that for the first time. So I'll give you a couple of minutes to solve A, B, and C by hand, and then we'll do D and E together. So if you discount the annual revenue of $16,000 at 10%, it's a positive sum of the present worth, $653. And if you discount it at 12%, then you get a negative present worth. So think about, why is that? Why does a 12% discount rate make it so that then the net present value is negative? It's because what you're doing is each one of the revenue amounts, if you move it towards time 0, it's being discounted at 12% for each step. So whereas the sum of the revenue was positive at a discount rate of 10%, that's because, if you move this 16,000 in year 5 to time 0, it's only moving 1, 2, 3, 4, 5 years at 10%. So it contributes a little bit to the present value, but if you're discounting at 12%, it's losing more of its value as you move it back through time. So the sum is negative if you've got the 12% discount rate. And the reason why that's significant is the rate of return would be somewhere between 10 and 12%. The rate of return is the interest rate that brings balance. It's the one that makes the sum of the inflows and the outflows equal when discounted at that unknown interest rate. Any questions on the hand calculation method here? So how do we confirm the same answer of, what is the rate of return using Excel? So, if I just start another sheet here in Excel, I'm going to have a value where I put in a guess interest rate starting with 1% and then a column of year, amount, PV of amount. And I'll translate the cash flow diagram so it's negative 60,000. And then I had inflows of 16,000 each year. And that, I need to put the amounts here. Year 0, 1, and it continues down through year 5. And the amount of 16,000 also repeats. So the function I'm going to use equals PV parentheses, and it gives you little hints of what it wants to see. So it's saying, tell me the rate. So I'll click here on the interest rate. I'm going to press the F4 button to put in dollar signs in the formula. And those dollar signs mean that when I move the equation down, it'll still always look in the same spot for the interest rate. And then comma, NPER, the number of periods. So N, I don't want those dollar signs to be there because I don't always want it to look in the same row. When I drag the equation down, I want it to look at the number of periods that the amount is being discounted. Okay, so skip over the payment field by just putting in another comma, because when I have the amount, I want it to recognize this amount as a future value. And so the minus of the amount is what I put into the equation to find out what's the present value of some future amount. Now the amount that's in year 0 is going to be discounted 0 years because it's already at the present. Now the formatting here, I don't like the style of formatting it does by default. The red drives me crazy and I don't like the parentheses, and so I'll just have it do currency, and then it changes it to something that looks a little bit more reasonable, I think. And then dragging that down tells me if I do a total by using the sum function equals sum and add all of that up. What did we have for the 10%? 0.1 for 10%, 652.59. So I was using the factor method and got 653. So that matches. And the 12%, 0.12, is going to be a negative value, negative 2323. And so the I that brings balance between the PV of inflows and the PV of outflows is, okay, so I'm looking for the goal. The goal is for this to be 0. And the way I achieve the goal is change I. Okay, so let me do that here in data, what if analysis, goal seek. Set this to 0 by changing the interest rate. All right, so it found that the rate of return is 10.425%. So that's one way to solve for it. And in part E, it also says that we have a function that's just called equals rate. It's been a while since I did that one. Let's use the rate function. Equals rate, and you put in parentheses, okay, and it wants to know NPER, so the number of periods. There was 5 periods. 5. Okay, what is the recurring payment, PMT? It wants to know what's the amount that was the annual series. So it was 16,000. And then what's the present value? The present value was negative 60,000. And then these other things are either optional. Yeah, the brackets means it's optional. So I'm going to close parentheses and see if it can solve. It says 10%, but that's just because it's not showing all of the decimals here. So if I increase the number of digits it shows, 10.425%. So it found the same rate of return as we did. And what it's doing in the background when you use the rate function is it's looking for what I value brings balance between a series of 5 payments of 16,000 and a single lump sum outflow of 60,000 that's already at the present. So it just kind of automatically in the background is doing all of the things that I set up here as a table and calculating the interest rate. So if you paid $60,000 and then you got 5 payments of 16,000, you're effectively earning a rate of return of 10.425%. Assuming that you reinvest the money at the same interest rate. That's the assumption of the internal rate of return. Any questions about A through E on the first one? We also have a question on the back side of the paper. So part 2. A is 8,000, P is 60,000. So if you divide P and A, you get 7.5. So look on the P/A column. If you go down and find out at what point, how many periods is it until you get the P to A ratio equal to 7.5. It looks like the crossover point is between year 14 and year 15. So what that means is that you need to have at least 15 payments before break-even occurs, where you've received as much value as you invested originally. So how many years do you have to own this equipment for it to be profitable? If you're buying equipment for $60,000 and it generates $8,000 a year and your discount rate's 10%, it would take 15 years for the equipment to become profitable. And let me show you a secondary proof of that with Excel. We've got our interest rate defined as 0.1 in this, 10% in this problem. Year, amount, PV of amount, and then I'm going to have a new column, which you haven't seen yet, called the cumulative PV of amount. And don't worry, I'll definitely have this done in 2 minutes. We've got 2 minutes of class time remaining. So I'm just going to translate this cash flow situation into a table. We don't know how many years we have to own it, so I'll do it down through 17. It's an outflow of 60,000 and then an inflow of 8,000, which repeats over and over. And we want to find out how many years is it until you're actually having a cumulative profit. So PV of the amount at our rate of 10%. The number of periods is whatever row we're on. I'm skipping over the payment field, and it's the negative of the amount. I need to change that to 60,000. And then double click here, and it'll apply the same calculations through all of them. Now the cumulative PV of amount, what I'm doing is I'm saying, starting with the first year, you're in the whole 60,000. But each subsequent year, it's the previous year cumulative amount with the present value for the row that you're on. So now if I drag that down, you'll see that the same thing that we noticed before, it's between the 15th and the 14th year that we go from a negative cumulative balance to a positive cumulative balance. So we'll do this on lots of occasions this semester. This is the break-even point. So the conclusion that I draw is the break-even occurs after 15 years. All right, it's almost 12:50. We're out of time for today. Just remember that your next assignment will be posted on Blackboard today, and it's due a week from today, on the 11th. I'll see you next time.